Okay, thank you very much. So what I'm going to talk is about what the seismic observations can teach us about nonlinear cell response in the shallow crust. This is a collaboration with several people that you see here, and the names here that you see underlying are the students have been working with us these last years. So the issue of nonlinearity is we have seen previous presentations where they show that now we are able to conduct very large simulations of predicting ground motion. And so this is an example where you can see, for example, the distribution of PGV in a surface in the Los Angeles area, for example, from the San Andreas Fault. But the question is how this distribution, which is used, is computed with the linear stress-strain relationship. How is it going to look if you have nonlinear side response? So I am going from the bottom to the surface. So the bottom is in this case going to be close, deep in the crust. So there are some simple examples where people have been studying nonlinear rock behavior. For example, using resonance experiments like it is done with soils, where they sweep different frequencies until they get to the resonance, and they increase the strain inside of the rock sample. And what they have observed is how the frequency starts moving or shifting to the left, to lower values of frequencies as the strain increases. So going even backwards in time, I see this is an example where the researchers have reported not the frequency, but the shift of the frequency. So they have negative frequencies here and positive frequency shifts here. When they use material like acrylic, which is a very strong material, you see that they increase the strain inside of the material and they don't get any shift. So basically this material is completely linear all the time. Sorry. When they use Berea sandstone, on the other hand, you start seeing shifting to the left, to low values of frequency, and it's even more pronunciated if you use Fontainebleau sandstone. So if you plot the shift of the frequency as a function of a strain, you get what some people in geotechnical earthquake engineering recognize like similar to the G over G max behavior. So this is the frequency shift. Now, there are some other experiments. This is done by some colleagues in Japan, in the Fukushima University, Katayama-san, where they use the Agi granite. And they have some samples where they are able to produce a small source impulsions, and they record, and they are polarized in order to get the P wave and also the S wave. And since they have the size of the sample and measuring the travel time, they can measure what is the velocity, P wave velocity, and also the S wave velocity here, as they increase the stress in the triaxial cell. So then you can observe that basically you have also a decrease as the stress increases. We look at this data, and we actually, what we did is we did a full waveform inversion on this data, and by doing that we obtain relatively similar results. However, something that is very interesting, I'm not going to show here, is that we also obtained the damping of the medium, and evidently, so what we observe is that the damping increases as the deformation or the damage in the sample increases. And then you probably are more familiar with soil nonlinear behavior from the laboratory as also. So this is a very complex behavior for granular materials where we can have some pore pressure effects. So then we have an excess of the pore pressure, increase of the pore pressure excess. We can have the development of large deformations, and we have phenomena of dilatancy effects, and they produce very large deformations as was shown by Ahmed before. So, but the problem with characterizing nonlinear soil behavior is basically what we have is different experiments, and what we report is the shear modulus as a function of the shear deformation and also the damping, of course. But here is an example where different experiments have worked wonderfully. So we have a common behavior, if you want, but with different regimes. So where we have is, for example, a viscoelasticity here, and we have a viscoelastic with hysteresis, and then we can have some pore pressure effects, and also we can have some damage here. And then we have almost a continuum. So the challenge that we have, for example, if we are thinking of doing or performing nonlinear computations at larger scale simulations, is how to understand the physical processes when only this envelope is known. No? So we have this information. So how are we going to get the parameters that are going to pass from this kind of a state to the next state as the ground motion increases? So the question is, so what are the physical changes in the medium during an earthquake? And can we detect these changes using observations? And is nonlinear deep or it is shallow? No? And another thing is this nonlinearity elastic, for example, nonlinear elasticity, or there is some damage so the material does not recover? So to do that, so I am going to the observations in seismology. So in seismology, you know, what we are interested is in measuring time. So with time, we locate the quakes, we see what is the P wave velocity, S wave velocity, etc. So this is a way of studying time, and it was done in 2008 in the Parkfield area where you have these stations. And you know that there were a couple of earthquakes in 2003, the San Simeon earthquake and the Parkfield earthquake in 2004. So studying the time that you see between the different stations using a technique which is called cross-correlation of the seismic wave field, Florent Brenguier and his colleagues were able to obtain what are the velocity changes that are in this area during several years, before the earthquakes and after the earthquakes. And what you see here, what you can see here is that during the earthquake, you have a drop of the velocity change. So here is a negative value. So this is the background velocity change close to zero, so nothing happens. And then you have the earthquake, and then you have a shift to the velocity change, and then you have a recovery. And then you have the Parkfield earthquake, and then you have a stronger shift because it was another earthquake, and also it's closer to these stations, and then it lasts even longer. And what is interesting is they plotted in this way because you can see that this recovery is related also to the aftershock activity in this area. So after the Tohoku earthquake, which was very well recorded in Japan, so you have here, so these are not the earthquakes, are the stations. So what you can see is that Wang in 2019 did the same thing, the cross correlation, in order to obtain basically the velocity changes in this area. However, what he did is he computed the different frequency bands, as you can see here, and you can observe that the frequency band close to 0.5 hertz produces frequency changes around 0.05%, velocity changes near 0.05%, but for frequencies below 1 hertz. And they are even lower at very low frequencies, but these are involving all the crust. Now, in 2019, also, we took advantage of the KickNet stations that you have here, and we studied this particular station, and I'm going to show the characteristics later, and using not only cross-correlation, but we correlate the station with itself, which is called the autocorrelation. And with the autocorrelation, you obtain the reflection, a reflection seismogram at the free surface. And this reflection seismogram allows us to study what is the velocity or the travel time between the surface and the first reflector to a given frequency band. So by doing that, we are able to track what are the frequency changes co-seismically, and also the velocity changes co-seismically here. And then you can observe in terms of values that in terms of the crust, we are 2 times order of magnitude higher. And also we see that there is a recovery, and the recovery doesn't get to the equilibrium even after 10 minutes of ground motion. So what do we do with this? When we obtain this kind of information, since the velocity change is basically related to the G over G max value, because we just square these results. So we can obtain in situ, and that is the interesting part, in situ decrease of the shear modulus as a function of the deformation, but also what we can see is as a function of time. So we reconstruct what is the deformation of the site just using the seismogram and we normalize by BS30. And we also corrected by the coseismic velocity change. And then in black here, in bold black, you can see the deformation. So that's what we plot here. But we also plot from the beginning up to the PGA. So you have the decrease of the shear modulus. And then we plot after the PGA. So you have the recovery time. And then you see that there is a difference. And if you put this as a strain phase, so you have the Hooke's law, and then you have in blue, you have the loading phase up to the PGA. And then you have the recovery phase, which is in red. So the question is, okay, so basically we don't have the same path in the recovery. So there is degradation. The thing is, what is the cause of this degradation? So we take advantage of the wildlife refuge liquefaction array. This is the new one where we have some accelerometers in there. And also we have some pore pressure transducers. This earthquake, this site recorded the 2010 El Mayor earthquake, magnitude 7.2, which was located 100 kilometers away from this site. So you have the time histories from 100 meters depth up to the surface. In the surface, you can see that you get almost 0.1 G, so it was a strong earthquake anyway. And then you have the pore pressure excess, and basically from 3.5 meters depth to the surface, you get a clear pore pressure excess. So by applying the same technique as I showed you before, what we obtain is that there is a very nice correlation between the pore pressure time history and also the velocity changes measured at that site. So in this case, we can say that basically that the site really responded due to the pore pressure effect. So what about long-term monitoring, especially using a permanent station? So I am going to revisit the station Ibaraki 16 in Japan. So this station is here. And it recorded 17 years. So I am using the data from the beginning of the station until 2020. And it recorded the Tohoku earthquake that you see here. And it has a very nice PGA distribution and magnitude. This site is interesting because it says it has 626 meters per second, BS30, but you can see that more or less than 10 meters, you have velocities around 300 meters per second. So using this technique, and now we improve this analysis by using different frequency bands. So this is our input. This is the recorded event, and we decompose this in different frequency behavior and velocity changes as a function of frequency. So you can see how much data we generate with recorded data. By doing this, we can clearly observe the frequency shift here, and also another frequency shift that we didn't see before, above 10 Hertz. And this is the same, but now we plot, instead of the frequency, we plot the velocity changes. In blue and also in green, you see negative velocity changes, and the velocity changes are concentrated in this area. If we plot this in this another way, so this is frequency as a function of acceleration, we have this kind of bell shape that I am going to plot here in a simplified way, and I am going to obtain the maximum value. So the maximum value is going to give me just what is the frequency shift, like people are looking at in rock samples. And if I identify these points and I come back to this diagram, I can extract what are the frequencies that are changing as a function of time, and also the related velocity changes. And then something is interesting here is that you see that the maximum or the peak of this distribution corresponds to the maximum or the predominant frequency of the response in this site. And then you can see how there is a degradation of the frequency as a function of the acceleration, which is similar to what it has been observed in rock samples. And these frequencies actually are affecting something like between 10 and 15 meters depth. So BS30 is coseismically affected. So now going to the catalog itself, repeating the same thing now, we can obtain what are the velocity changes as a function of frequency and time, for example, for accelerations less than 10 centimeters per second square, and also for the accelerations greater than 10 centimeters per second squared. So the first thing that we can observe here is the variability, the strong variability that we have after the quake. So this is center, the 0 time is the Tohoku earthquake. So this is before background, and then you have the Tohoku earthquake, and then you see up, down, up, down, up, down, and something that I don't know what happened here is after 1,000 days, the high frequency here disappeared. But this does not happen in the north-south component. So this is a mystery. And then when you have with the higher acceleration, something that is very interesting and very nice, you see the recovery. So you see the recovery in these two frequencies. So then you have so this is going to be related to the close to 10 meters depth, and this is going to be related to the first 2 or 3 meters depth. So that is quite nice. But the difficult part is to answer is what is the recovery, when the site recovers. So just to show you, this is, I am computing here is the transfer function for the period before the Tohoku earthquake is in blue. This is the transfer function in red for the 1,000 days of the Tohoku earthquake, and then after, so this is in red. So you have a variability. This variability actually can we measure if we measure also the variability at each frequency time, and what we obtain in average is between -5 and 5%. So our BS30 that we usually suppose that is constant varies between 550 and 700 meters per second. So the final thoughts. So yes, the shallow soil behaves nonlinear, so we could have even larger amplitudes because, and thanks to the nonlinearity, we have less higher values. So the velocity changes are related to the nonlinear processes in the shallow crust. However, we still don't know why or what is the mechanism behind them. So an important thing is that these are in situ observations. So these are very complementary with the laboratory data. You know? The velocity changes last several years for frequencies below 1 Hz, and they mobilize the crust. However, they are relatively small in terms for practical purposes in engineering practice. However, the surface, near surface effects have several values of magnitude, and they have a strong variability in time. Something that I would like you to keep in mind is that BS30 is not constant and it has an uncertainty. And also what we have to be careful is only using BS30 without knowing the soil column, because this might be hiding the presence of soft soil or shallow depths that might be prone to nonlinear effects. And finally, probably some of you are working on the kappa, what is called the kappa value or the high frequency attenuation. Since nonlinearity is very well observed in this kind of material, so it's very difficult to assess what is the meaning of this kappa value. Okay, thanks. I hope that I finish on time.